thing that we were concentrating on. But other sectors, people want to do building, those that really are serious go on. Yeah. The Petroleum Training Institute is a committed, experienced, purpose-driven, and well-structured organization. It has 2 campuses and a well-equipped conference center with accommodation and lecture halls, and a conference hall capacity of over 1,000 persons. This, we have said it, it hosts the NDT, National NDT Center. She is an authorized training body of the Nigeria Institute of Welding, which is an arm, an authorized body of the International Welding Institute. Then she's also an approved, we have a body now, we are trying to take Africa. Africa is trying to take their place. So we have this, the Welding Federation, Africa Welding Federation, so TWF. I think we are going for the 3rd assembly now in Addis Ababa by April next year. The 2nd assembly was here in Lagos in March. So we are an authorized training body of the TWF, and also we have with national skill acquisition, the federal government has come up to say we must qualify skills. So we are also a center for the National Skill Qualification Skill, which is the NSQ. We have all the expertise to do the work, but particularly we want collaboration with INDT. So closer collaborations will enable us to do better. Go on. Conclusion. Collaboration is necessary to synergize and carve a niche in NDT practice to preserve our national assets. We therefore call on the government through NNPRA and others for properly equipped funding of the National NDT Center located in PTI. Collaboration with INDT Nigeria will be a way for the fulfillment of the mandate to train and conduct research in NDT and science and technology. The center and INDT with other stakeholders can play a proactive role in identifying industry problems and profile solutions, legislate NDT standards and laws to govern the industry, develop NDT education and training curriculum. So thank you for listening. Thank you.
Let's have another resounding round of applause for Engineer Grace Okekute Ehimona, representing the Principal CEO PTI at Petroleum Training Institute for that presentation. The conversation continues.
Where is it? Where is it? Here's my flash. You sure? So that's not my flash.
All right, distinguished ladies and gentlemen, at this time I must call on our the next person for the technical presentation to come talk about robotic systems applying to non-destructive testing and structural integrity inspections.
Okay.
Ladies and gentlemen, let's make welcome the person of Dr. Bello Salihu, Chartered Engineer, Fellow Institute of NDT, PCN Level 3, and Chief Technology Officer, Subsea Robotics. Let's put our hands together as he
Show me
approaches.
a PowerPoint.
But
There's a PowerPoint here.
while he makes his way down here, let me tell you about our next presenter. Dr. Bello Saliu is a chartered engineer and a fellow of the British Institute of NDT, and he holds level 3 NDT certifications with both PCN and CC. He is the Chief Technology Officer of Subsea Robotics and has over 30 years experience delivering technology driver solutions in the global oil and gas industry in the areas of advanced NDT and robotics. Ladies and gentlemen, let's have a resounding round of applause as he approaches.
There's a PowerPoint here.
You're welcome.
Thank you, everybody. I will try to get the presentation ready. I have to transfer it from a Mac platform to a Windows platform, so trying to see if we can get it up. Subsea Robotics is in the business of delivering advanced non-destructive testing technologies at depth. We go to the depth of NDT inspections, no matter the water depth, using robots. Most of all who are involved with underwater inspections, subsea inspections, know that there is a limit where the divers cannot go. And that limit is normally between 150 to 200 meters of water. Beyond that limit, we need something else that is not physiologically limited, and that is a robot. So since the advent of deep water exploration, we have had assets placed in 500, 2,000 meters, 2,000 meters of water that we can only inspect using robotics. Okay, so to the next slide, please.
Next slide.
So we open this because advanced NDT, we are going to talk about something novel that is going on, and that is NDT 4.0. We'll break it down, but to do that, we have to understand why it has come to be, or what has enabled it, and that is digital transformation. To discuss digital transformation, previous slide. Previous slide. Yes. No. Previous slide again. Yes. So please press it. Once. Okay. Without it being shown on the screen, digital transformation takes us to 3 aspects. There's the digitization, there's the digitalization, and digital transformation. Digitization is when we have data collected manually, and that data collected manually is not in any digital format. Say, for example, for NDT practitioners, which we all are here, you perform an MPI, magnetic particle inspection of paper. Digitization means for you to put it on your report, you have to scan it in. So you digitize it. Digitalization, which is the second stage, is when you have that MPI equipment enabled to give you that data digitally itself. Yes, thank you. So that's the digitalization, just hit it? Yeah, is talking about getting that data in its original form as a digital data. And then the final one is digital transformation, where the entire process, zero, which brought about mass production, about 100 years later, we all remember the Henry Ford, assembly line, okay? And we can do that because we have electric power, and we have production, the demand is there. Then we go to technology 3.0. This is the advent of this started in like the 2000s when computers become integral to what we do. Now we have computers, things are being automated, we have production and we have electronics. This is technology 3.0. Now we go to the last one on this slide. That's technology 4.0. 4.0, we have this type of physical systems. The last speaker here was talking about grid collapse. Yeah, the last speaker here was talking about grid collapse. When you have a cyber-physical system, is that system where the physical asset itself is communicating with another physical asset or to a system using the cyber technology online. So, say for example, we all know I live in Milton Keynes, near London. I can virtually from here start my washing machine because it's been enabled. Use my phone, a physical system, start another physical system using the enabling technology. Okay? And what has brought that about? Technology 4.0. And what powers technology 4.0? Take it slowly, one tap at a time. What enables technology 4.0? The first one is robotics, which is the business we are in. The second one is simulations. We can learn by simulations, we can do by simulations. The third one is system integration. We can integrate system into a whole to deliver a service or to deliver a task. The next one is Internet of Things. That thing I said about my washing machine, that's Internet of Things. It has an IP address. My phone has an IP address. They can communicate. So the next one is, we've lost it there. I know one of them is cloud computing. The other one I can remember. So let's go to the next one. And the next one, additive manufacturing. Additive manufacturing is actually 3D printing. That I can design something here today, have it made in China tomorrow, and have it delivered to me. The next one is augmented reality. Enables us to teach, enables us to work, enables us to so many things. We'll come back to that a bit later at the very last slide. And the last one is big data. Okay, the one I mentioned down here that I can remember, apart from cloud computing, is cybersecurity. Because all of these units need to be secured. Otherwise, it's not going to work. So that's technology 4.0. That is driving NDT 4.0, as we will see in the next slide. Hit it again? Good. Hit it again. So Vrana, one of the zero, said this, that the concept of cyber-physical non-destructive evaluation, including non-destructive testing, arising from Industry 4.0 is arising from Industry 4.0 digital technologies, the one we mentioned here, and inspection methods and business models. He also said NDT 4.0 evolved in conjunction with Industry 4.0. Let's go on. So this is where we are at on that. I've broken this slide to show mechanical, the technological epoch up there, the industrial epochs, and the NDT epochs. Industrial revolution is technology 1.0. We had the mechanical, steam engine, and energy. What we could do then, and that's why technologies like magnetic particle inspection as MPI and dye penetrant are called Victorian technologies. They are not in any way digital. What we can only do with them, what they only do to us, it aids our senses. If you take a component that is cracked, you look at it very, very, very hard, you will actually see the hairline. But we don't have time for that. So you have a system where you energize it with magnetism, you put some magnetic particles, and boom, you can see it. So it kind of amplifies what your senses can do. Then technology 2.0, which is technical. We have electrical energy, we have mass production, So, but then we still have analog systems. We have developed a bit, but they are still analog, like our typical UTA scanner. Your RT, in which you have to use film. Okay? So these are analog systems that are not digital. And then technology 2.0, with the advent of microelectronics and data processing, we can now have digital systems like the digital radiography, like the digital camera, like the ACPD. ACPD is actually the forerunner of my specialist NDT technique, which is ACFM, for crack detection. So when you use an ACPD machine, you see it on the screen, you record it. You don't collect it digitally. And now we're at technology 4.0. We have technology 4.0, where increasing digitalization means we can do things digitally, transparency of information, decentralization making. We have ACFM, we have PAUT, PAUT is phased array UT, post-eddy current testing, computer radiography. These are all computer-based. So you see how we have moved in a span of how many years, how we have moved digitally to a point where almost all advanced NDT, which is this other keyword in my presentation, robotics and advanced NDT, we have seen how we come to advanced NDT now, which is ACFM, PAUT, PCT, computer. These are not the only advanced NDT techniques. There are many like that. Okay, we move on. So we go to robotics. Robotics is the intersection of science, engineering, and technology that produces machines that substitute or replicate human actions. Or some will say programmable machines that assist or mimic human actions. So you have a robot. We've seen the robots on the production line in TV. And then we don't have that. Okay, so we see the robot on the production line. It does a lot of things, but everything a robot does, mostly, unless if it is, specifically created to do that and in a place where you cannot change what it does, like in the Mars rover, it's already in Mars, a robot will have 6 degrees of moving, 6 degrees of motion. You have the first degree, which is the S-axis right there at the bottom. It allows the robot to move this way. So it swivels, it turns. The second degree, which is the the second axis, allows the robot to move forward and backward. Then you have the next axis, which allows it to move this way. And then you have the U-axis right by the neck that allows the handle to move. And then finally, you have on the arm itself, you have that motion that allows it can move, it can accelerate. It can detect temperature. It knows where it is by position. You can put an odometer on it and it counts how many places it's gone to. It can touch, it can force, it can produce a magnetic field, it can produce sound. It does all this through sensors. We'll look at a few of them. And then it can plan a task. So 3 points here. It can sense, it can think, it can act. Part of the thinking is it can plan a task. It can learn something, especially now with AI and machine learning. It can process data, it can plan a path, and it can plan emotion. And the last one is the act, where from all this, it can output information, it can speak, like we mentioned, it can send text, it has wheels, it can move, it can activate those wheels. So these are the 3 things of a robot. Next one. To do that, the key components that allow a robot to do that are its power conversion unit. We start first at the bottom there, which is the user interface. We can't read it because of the way the screen is set up, but we have the user interface at the bottom. The user interface interacts with the controller. The controller interacts with the sensors and the actuators and the power conversion unit. You remember what I told you about the axis? Those are the actuators. That is actually what moves. You remember what I told you about temperature or reading weight or stress? That are the sensors to do that. So everything we mentioned to be able to do that is either a mechanical construction, an electrical component, or a computer program. Now, computer program enables the robot to think or to take instruction or give out results. Now, computer RPAS, which is robotic process automation systems, or robotic process automation software. Okay, examples of RPAS is the ROS, which is robotic operating system, the Arduino, the VxWorks. I mean, today with Raspberry Pi, we all know Arduino. Okay, all the tools that connect to Raspberry Pi are mostly Arduino tools. And the last here is zeros and one piece of data is actually a car using the fully connected layer of a machine learning system. A robot can know from here that if it needs to get to this goal, it can achieve that without hitting. Then it has the mapping, which it does with something called LiDAR. We know radar. Radar is what tracks the aeroplanes. LiDAR, it will do the same using laser. So instead of radio signal detection and ranging, this is light detection and ranging, which is LiDAR. Next one, please. Okay, so these are all the tools the robot has. Not all of them, many more. But these are the ones we can use to get all those. Next. So, on structural inspections, why is robotics all of a sudden important? Why is it the buzzword? It is said that now, if you go to a major IOC, I don't want to mention the name, and you said you have something to do underwater task or something high up you want to do, they will only commission you if there is no robotic option to it. Saudi Aramco recently budgeted about $10 billion to forward it. Okay, so accessibility, detachment, safety, cost. It is much cheaper to put a robot in water than to put a diver in water. It is much safer for a drone to look at the flare than set up scaffolding and put up a human being. And it is repeatable. It's a machine, it doesn't get tired. I had this argument the other day with my wife. I'd rather drive, an autonomous vehicle than have a human driving, because an autonomous vehicle will never crash or will never hit another vehicle, because it doesn't have the sense to know that, I need to avoid that vehicle, and it's already programmed in it, so it doesn't work with human cognition. Okay, next one, please. So, advanced NDT is the use of wide range of NDT techniques based on innovative technologies to inspect and analyze anomalies and assets with less disruption to operations. Compared with conventional NDT, it provides quicker results and improves the accuracy while being cost effective. That is advanced NDT. Now, I don't want to bore you with the conventional NDT, UT, RT, PT, no. Conventional NDT are specialist techniques that are adaptable to digitalization or digital transformation. We go. So, in our company, like I said, we can run so many advanced NDT examples. But in our company, we have 4 that we use. One is acoustic resonance technology. Very simple technology. It sends very low frequency sound waves onto a structure. The sound waves hit the structure resonates, and we read this resonance back. Reading it back will tell us where it is faulty or where it has a problem. That is acoustic resonance technology. Okay? We use it for route integrity, flooded member detection assessment, and all of that. This is the machine we use for it. It's the main machine we have in our company. is actually our bestseller. That's why it is on the very first page of my presentation. The second one is alternating current field measurement. Very easy. You send an alternating current onto a surface. This alternating current, by Faraday's law, gets converted into magnetic field. And this magnetic field, when there is a disturbance or a crack, it gets disturbed, and you read that disturbance digitally. Before you move, we'll go back. Can you click on the picture, please? Click it again. The machine you saw, that is us doing a line test on the machine. This is one of the training we give our operators before we send them offshore or before we send them to control the machine. And that's a younger version of myself. Because we need it to be able to render what it has faster and much clearer in a digital format. So it has very high resolution topology mapping and it is flexible to complex geometries. These are the advanced NDT methods our company uses. Other companies may use others, but these are the ones we use. NDT generally is a toolbox business. You look at all the failure mechanisms you want to track and everything. These tools will give us everything from volumetric to surface. We can detect them all with this. Next one, please. Good, stop now. Click on the first one, please. Artemis. We are now coming to robotics. Proper robotics. Completely, totally robotics, controlled from the top. That is the scanning. This is what it's doing. It's sending signals in, and this is PEC. This is pulse eddy current. Pulse eddy current gives us the ability to inspect through thick coatings, apart from concrete. I mean, up to 100 millimeter of coatings. We don't need you to remove the coatings. 3LPP, all sorts of coatings. We can look through them. Okay.
Next part, and then the next one.
Nightcrawler. Click on it. This is the one we saw at the beginning that I was playing with in our in the lab. Yeah, that is it at work. It is going to follow the weld line now, controlled from the top, and that is it doing the ACFM inspection on that weld craft. That's the last one. After this one, the next one is the last one, I think. Yeah, the line scanning. Go ahead. Next slide. Good. So we're almost at the end now. At the beginning, we started from what happened before the Industrial Revolution. Thomas Newcomen, 1700s, invented the engine. then we went to the second technological revolution, the third one, the fourth one. The future is actually now. We are now at technology 5.0, started 4 years ago, okay, in which we have the human-robot collaboration, and we have cognitive systems, customizations. We are talking about full autonomy. We have AUVs now, autonomous underwater vehicles that we can send down to go and do work for us. We can give a robot a work program, and it will go down and execute our program. Okay. So we are at technology 4.0. Looking at the other slide I made, at 5.0, we now move from autonomy, that systems can take decisions. We've been empowered by machine learning, we've been empowered by robotics, we've been empowered by so many things that we can now create digital twins. As I mentioned here, apart from advanced NDT, you have autonomous aerial vehicles, autonomous underwater vehicles, we have digital twins, you have the metaverse, where in that slide I made, I showed you the augmented reality where you wear the glasses. You can now wear a glass somewhere in Lagos and look at your structure through a digital twin in Lagos and have a system work on it offshore Nigeria. That is very, very practical, is very possible, is no longer science fiction. This is just buttressing the point. This is as written there, that is the Fugro Remote Operations Center, somewhere in the heart of Aberdeen, Scotland. And I happened to consult for them in September 2022. In this particular project at the Fugro Center, we were using in red an uncrewed surface vehicle, USV. This USV is on a riverbank in Netherlands. That USV in it, that vehicle, that boat in it is an electronic remote operation vehicle, ROV. And from this center in Aberdeen, we will move the vehicle on its own, unpiloted by a human being. We will move it from the coast, from the harbor, and it goes into the water and goes to the location of the pipeline. At the location of the pipeline, we will release electronic electronic ROV without a person being there, and it will conduct an unmanned pipeline inspection. That was 2 years ago. We had teething problems then. I know they have sorted those problems now. But this has been enabled by NDT 4.0 and everything I mentioned about Industry 4.0 to you. Okay? So our name is Subsea Robotics, Lagos, and you can reach us at Dello at subsearobotics.com, and our partner is TSC Subsea, and that is the end of our presentation. Thank you very much.
Distinguished ladies and gentlemen, I will say that's an eye-opener, and of course a very lovely presentation there. Robotics. Well, I hope to delve into one of these days. Alright, so without much ado, and I'm believing this is going to be our final presentation for today. Okay, we still have some more anyways. They're all interesting, great conversations, I must say. Alright, so we shall be having another technical from one of our speakers to talk about predictive maintenance for management of aging refineries in Nigeria. It is at this time that I must call on Engineer Andrew, that's Engineer Dr. Andrew John, a member of the NDT and a senior lecturer, PTI. Let's have a resounding round of applause as he approaches.
Thank you once again. All protocol do well, sir. So I'll be presenting on NDT 7.0 since Dr. Bello has presented